From a country that once lost 1/3 of its farmland to desertification, China has now risen to become a powerhouse in high-tech agriculture, where robots, AI, and self-operating farms run around the clock, creating an ecosystem worth more than $1 trillion USD. In today's video, you'll see how China has rewritten the rules of the game, using technology to reclaim lost land, turn deserts into farms, transform rocky mountains into greenhouses, and build an agricultural sector capable of competing with the United States, even catching up with the technological pace that Washington has held for decades. Nearly 1/4 of China's territory is desert, where scorching winds and drifting sand make it extremely difficult for crops to survive. The Taklamakan Desert alone spans more than 330,000 square kilometers and is so dry that it's nearly devoid of life. Yet instead of abandoning this harsh land, the Chinese took an unexpected approach. They began growing cotton. To grow crops in the desert, China relies on an entire system of specialized technology. High-powered tractors plow, level, and compact the loose sand into stable, straight rows, reducing sand drift by up to 70% and helping the soil retain moisture. After that, they lay down agricultural mulch film stretching for kilometers, a solution that can cut water evaporation by up to 90% and retain enough warmth for seeds to germinate. Thanks to the combination of heavy machinery and modern agricultural materials, the once shifting desert surface is transformed into ground stable enough for cultivation. Once the sand is compacted and covered with mulch, seeds are planted into small openings. A drip irrigation system immediately delivers precise amounts of water, helping the seeds germinate reliably amid the desert's extreme dryness. After months of enduring scorching winds, extreme temperature swings, and sandstorms capable of wiping out entire fields overnight, the desert cotton farms finally reach harvest season. From the now stabilized sandy ground, China moves on to the most critical phase, tech-driven harvesting. Bright red cotton harvesters, from Tianya machines to the John Deere CP690, advance in perfect formation like a mechanized army, sweeping across thousands of hectares. Each machine handles 10 to 12 tons of cotton per hour and compresses it into dense modules within minutes. With GPS, ground sensors, and automated control cabins, entire fields stretching tens of square kilometers require only 3 to 5 engineers to monitor everything remotely. Lacking the fertile land that the United States possesses, China has been forced to build its advantage through technology, turning deserts into industrial-scale agricultural production lines. It is precisely the harshness of nature that pushed them to develop a generation of powerful, highly precise machines, capable of transforming uncultivable land into one of the world's major cotton hubs. Leaving behind the white cotton fields of the harsh desert, we continue our journey to lush green rice paddies, where the power of machinery and automation is reshaping the way humans farm. For centuries, rice transplanting was one of the toughest tasks for Asian farmers. Bending over in flooded fields for hours, planting each seedling by hand, and managing to cover only a few hundred square meters per day. But today, everything has been completely transformed thanks to automatic rice transplanting technology. Modern rice transplanters like the one you see here operate as large-scale, agricultural robots. At the front sits a platform holding dozens of seedling trays, while at the back, a system of mechanical arms continuously lifts, separates, and plants the seedlings into the field at a steady pace. Each machine can handle 1 to 2 hectares per hour, equivalent to the workload of 40 to 50 traditional laborers. RTK GPS technology allows the machine to move in perfectly straight lines, with a margin of error under 2 centimeters, ensuring nearly perfect spacing and density between each plant. Depth sensors automatically adjust the planting feet, so the seedlings are neither too deep nor too shallow. All of this happens while the operator simply sits in the cabin, monitoring the parameters through a digital display. As the rice grows and enters the tillering stage, technology once again takes over the farmer's labor. Automatic spraying drones follow GPS routes, dispersing ultra-fine mist across entire hectares within minutes, protecting the rice evenly, quickly, and with almost no manual work required. And as the green rice seedlings grow taller, the paddies turn golden. Harvest season has arrived. Unlike wheat harvesters in the United States, which operate on dry, flat, and firm fields, rice harvesters must work under completely opposite conditions: deep mud, soft ground, low traction, and a high risk of getting stuck. That's why their technology is specially designed. Wide track rollers to distribute weight, automatic balancing systems to prevent tipping, and a cutting threshing mechanism that works reliably even when water reaches halfway up the wheels. A modern rice harvester can process 0.6 to 1.2 hectares per hour, replacing the labor of 20 to 30 workers. Inside, the threshing and fan system separates grain from straw within seconds, depositing the rice directly into sacks or sealed containers to minimize moisture. Thanks to sensors that monitor soil moisture and sinking, the machine automatically adjusts its speed to avoid damaging the remaining stalks. While wheat harvesters in the US run like steel trains across dry plains, in Asia, rice harvesters resemble mud-crawling machines, fine-tuned with precision for every movement. As a country warming at twice the global average, having recorded temperatures above 50 degrees Celsius in Xinjiang and experiencing extreme rainfall that forces millions to evacuate each year, China has been pushed to accelerate greenhouse agriculture to safeguard its food security. In modern greenhouse complexes, vegetable production operates like a clean food factory. Seeds are dispersed by vibration machines with less than 1% error, incubated in perfectly climate-controlled chambers, and then transferred into the main greenhouse. Here, high-pressure misting systems maintain stable humidity, LED lights adjust to each growth stage to boost development by 20 to 30%, and robots continuously move trays to optimize light exposure and airflow. All data, from leaf color to growth rate, is analyzed by AI, which automatically fine-tunes environmental settings by the hour. The vegetables grow in conditions so clean that pesticides are almost unnecessary and contamination risks are virtually non-existent. When harvest time comes, robots pull the trays into a sealed processing area where the produce is washed, sorted, and packaged immediately. The entire journey from seed to table remains within a fully controlled technological chain, reflecting the advancement of Chinese agriculture amid an era of harsh climate conditions. While this model delivers consistent, year-round, and safe produce, its cost is 1.5 to 3 times higher than traditional farming, forcing older cultivation methods to evolve or risk being left behind. Under the pressure of harsh climate conditions and a surging demand for clean food, China is not only building vegetable factories inside greenhouses, but also deploying robots directly into the fields, replacing labor-intensive, sweat-driven tasks with precise, fully automated systems. Apple harvesting has long been an extremely labor-consuming job, picking each fruit by hand, risking bruised skins, and requiring hundreds of labor hours for just 1 hectare. That pressure has driven many orchards to adopt apple-picking robots, machines that precisely replicate the delicate movements of human hands, but at far greater speed. Equipped with 3D cameras, ripeness sensors, and AI recognition, these robots can identify each apple in a fraction of a second. Their silicone grippers perform a gentle twist-pull-detach motion, allowing them to harvest 1,200 to 1,500 apples per hour, 4 to 6 times faster than manual labor. Once picked, the apples are immediately transferred onto conveyor systems for automatic size grading. With the ability to operate around the clock, apple-picking robots are transforming orchards spanning hundreds of hectares into nearly fully automated harvesting lines. The hills of Zhejiang and Anhui have long been the cradle of China's finest teas, but traditional tea picking is full of risks. Clinging to slippery slopes, performing meticulous hand movements for hours, and facing a growing shortage of young labor. These challenges have driven the rise of tea-picking robots. These machines use high-resolution cameras combined with AI to identify individual tea buds in fractions of a second, distinguishing young leaves from mature ones with an error margin of less than 5%. Their mechanical arms are equipped with micro-vibrating cutting blades that mimic the skilled pinch and pluck motion of experienced pickers, ensuring the tea buds retain their shape and freshness. Each robot can handle the workload of 20 to 30 workers and can operate continuously even on terrain that is difficult for humans to access. As a result, traditional tea hills are gradually transforming into high-tech, highly precise harvesting systems, consistent, stable, and surprisingly efficient. Known as the nutrient reserve of the cold season, cabbage is one of China's key vegetable crops. And while many European fields still rely on manual labor, Chinese farms have taken a completely different path, harvesting with machines as if operating an industrial production line. Cabbage harvesting is notoriously labor-intensive. Each head must be cut by hand, requiring thousands of repeated bends and lifting tens of kilograms every hour. This difficulty has made cabbage harvesters the inevitable solution. These machines use high-speed hydraulic blades to cleanly slice each cabbage in a single motion, then lift it onto a moving conveyor, where an automated trimming system removes old outer leaves on the way up. From field to storage bin, the entire process runs seamlessly without a single human hand involved. Each machine can harvest 8 to 12 tons of cabbage per hour, tens of times faster than manual labor. With ripeness sensors, anti-sink systems, and self-balancing controls, the harvester moves smoothly across soft soil, transforming the entire field into an industrial-scale harvesting line where speed, quality, and precision are maintained down to every meter of land. When people think of blueberries, they usually think of Europe. But in China, this fruit is entering a new era: large-scale cultivation, high-value wine production, and fully mechanized harvesting. For years, blueberries were a harvesting nightmare for Chinese farmers. Tiny fruits, easily bruised, picked one by one, and requiring hundreds of labor hours per hectare. As processing demand surged, manual harvesting quickly became the biggest bottleneck. This led to the rise of specialized harvesting machines. Instead of relying on human hands, these machines use high-frequency vibrating rods to detach ripe berries from the branches, tuned precisely so they don't damage the plants. The falling berries are caught by soft catch plates and then transferred directly onto conveyors for preliminary sorting. Thanks to this mechanism, the berries remain almost entirely unbruised, preserving their quality for processing. A single harvester can handle dozens of tons per day, replacing the work of an entire labor crew. Equipped with sensors and navigation systems, the machines move accurately between each row, operating continuously like an outdoor production line. As a result, vast blueberry orchards can be harvested faster, cleaner, and with greater uniformity, meeting the standards for both fresh consumption and premium blueberry wine production. Farmland are dedicated exclusively to tea cultivation, concentrated mainly in Japan's midland and mountainous regions such as Shizuoka, Uji, Kyoto, Kagoshima, and Aichi. Despite accounting for only a very small share of the country's total agricultural land, the green tea industry generates hundreds of millions of USD annually for Japan. Rather than pursuing mass production, green tea has risen to become one of the 4 high-value pillars of Japanese agriculture, alongside rice, premium vegetables, and specialty fruits. It has helped Japan maintain its #1 position globally in matcha and firmly assert the prestige of Japanese agricultural products on the world market. The secret behind the vibrant jade green color and the irresistible umami sweetness of Japanese matcha lies in its shade-growing technique. About 3 weeks before harvest, artisans cover entire tea fields with layers of black netting or straw, blocking up to 90% of sunlight. In the darkness, the tea plants are pushed into survival mode, forcing them to produce a massive amount of chlorophyll to absorb the scant remaining light. At the same time, this process drives a sharp increase in amino acid levels, creating the matcha's signature calming effect. The result is a tea leaf with highly concentrated nutrients, an almost mesmerizing green hue, and a smooth, gentle sweetness, something no tea grown under direct sunlight can ever replicate. During the harvest season, typically in early May, the intelligence of Japanese agriculture is clearly demonstrated. To meet the global surge in demand, with more than 2,000 tons of tea exported to the United States each year, specialized tea harvesting machines from popular lines such as Valiant and Ochiai have become the key for Japan to optimize production. Operating by enveloping entire rows of tea plants, using curved cutting blades to create a uniform dome shape, and simultaneously employing high-pressure air streams to blow freshly picked leaves directly into collection bags in an instant, each machine can process over 1,000 kilograms of green tea per hour, fast, consistent, and efficient, while still maintaining the quality standards required for industrial processing. Once inside the factory, the tea leaves are immediately steamed to lock in their color and halt the oxidation process. After being air-dried to become tencha, the most delicate step begins, removing the leaf veins. All stems and veins are completely discarded, leaving only the purest part of the leaf. This is precisely why Japanese matcha powder is always silky smooth. Finally, the product is finished using massive granite stone mills. To preserve its highly sensitive flavor, the stones must rotate extremely slowly to prevent heat from altering the aroma. It takes a full hour of continuous grinding to produce just 30 grams of powder, so fine that it seems to melt instantly upon touching the tongue. Despite competing with low-priced matcha, Japan maintains its position through extreme meticulousness. This craftsmanship has pushed the price of premium tencha to $56 per kilogram, while ceremonial-grade matcha can reach hundreds. Despite not leading global rice production like Thailand or Vietnam, Japan stands out with premium varieties such as koshihikari, valued for their exceptional stickiness, subtle aroma, and natural sweetness. The journey of creating glossy rice grains begins with meticulous care right from the sowing stage. Instead of direct seeding into flooded fields, farmers use standardized plastic trays filled with loose, nutrient-rich soil. Once the seeds germinate, seedlings are evenly distributed at precisely controlled densities to ensure ideal growing space. During their first weeks of life, young rice seedlings are strictly protected like in mini greenhouses by covering the fields with white plastic sheets. This layer stabilizes temperature and humidity, allowing the seedlings to grow healthily despite cold winds. When the time is right, the root systems intertwine tightly to form a solid mat, enabling farmers to lift entire sections of seedlings without damaging a single root. Next, these seedling mats are loaded onto automatic rice transplanters. The machine separates each small clump and inserts it into the mud at a precise spacing of 30 centimeters per row. Straight-line planting helps optimize air circulation, ensure even sunlight exposure, and reduce pests and diseases. Although not a rice superpower when it comes to automatic rice transplanters, Japan is currently one of the world's leaders in technology and mechanization. A Japanese rice transplanter, represented by models such as Yanmar, can handle at least 1 to 1.5 hectares per day, working 10 times faster than manual transplanting, a method still commonly used in countries such as Vietnam and India. After about 150 days, when the fields turn golden, modern combine harvesters move in. Compared to combine harvesters used in the United States, Brazil, or Australia, Japanese machines are much smaller, with a capacity of only about 1/5. Yet this compact size is precisely their advantage, allowing them to operate flexibly on Japan's small, fragmented, and soft-field terrain. These machines perform a closed-loop process, cutting the rice, threshing the grains, and bagging them directly in the field, while simultaneously chopping straw and returning nutrients to the soil. As a result, a single machine can harvest and thresh 1 hectare of rice in under 3 hours, replacing the labor of dozens of workers. While Thai jasmine rice, widely regarded as the gold standard of Asian rice, sells for around $2 per kilogram, premium Japanese rice is often priced at over $20 per kilograms, distinguished by its plump, round grains, high stickiness, and the ability to retain a rich natural sweetness even after cooling. Many people think grapes should be soft and juicy, but Shine Muscat, a premium peony grape from Okayama, the sunniest and least rainy region in Japan, features a firm, jelly-like crunch and a sweetness reaching 20 degrees Brix, about 1.5 times higher than ordinary grapes. The secret of Japanese farmers lies in calculated sacrifice. From the moment the vines begin to flower, they prune ruthlessly, allowing each branch to retain only a single best grape cluster, forcing the plant to channel all the nutrients, sugars, and essence, originally meant for dozens of other clusters, into one single entity. Not stopping there, they continue to hand-thin each small grape within the cluster, ensuring enough space for the remaining grapes to grow large without being crowded, while allowing air and sunlight to reach every gap. Not only that, each Shine Muscat grape cluster is wrapped in a special paper bag while still on the vine to block insects, harsh UV rays that can scorch the skin, and even rain droplets that may cause mold. This is precisely why Japanese Shine Muscat grapes have smooth, glossy skins that can be eaten directly, without bitterness or chemical residue. When harvest time arrives, instead of cutting in bulk, farmers measure the sugar content of each individual cluster using handheld meters. Only those that meet the standard are allowed to be picked. Each grape cluster is carefully handled and harvested entirely by hand, like a living piece of jewelry. Farmers use specialized scissors to cut each stem with absolute precision, avoiding any movement that could damage the delicate skin. Once picked, every cluster is immediately placed into a cushioned tray to preserve its perfect shape and natural gloss. There is no mass harvesting, no stacking, only meticulous care at every step. With the enormous labor costs involved in meticulous hand cultivation, each premium Shine Muscat grape cluster can fetch $100 to $200 USD at auctions or in high-end supermarkets. Leaving the mainland behind, seafood has become the second front through which Japan has built a luxury empire worth around $2.5 billion USD annually, turning the country into one of Asia's leading sanctuaries for high-end seafood. Among more than 400 commercial seafood species, bluefin tuna dominates the premium segment, making it the most sought-after ingredient in the world of sushi and sashimi. The otoro, the fattiest cut from the belly of a top-grade bluefin tuna, can be priced at $30,000 to $50,000 USD, comparable to a luxury sedan such as a Mercedes-Benz E-Class, and sometimes even higher at early-year auctions. Traditionally, bluefin tuna are caught during the winter season, concentrated in the northern Pacific Ocean, using methods such as handline fishing or longline fishing to preserve meat quality. However, in response to rising global demand and the growing risk of depleting natural stocks, offshore bluefin tuna farms have emerged, with Japan being one of the pioneering countries. These kings of the ocean are raised in massive circular cages in deep waters, where currents, oxygen levels, temperature, and feeding regimes are strictly controlled. Automated feeding systems precisely distribute feed, allowing the fish to grow evenly and achieve an ideal fat ratio. Thanks to advanced offshore aquaculture technology, Japan produces more than 10,000 tons of farmed bluefin tuna each year, with an estimated value of at least $700 million USD, securing the country's position as the world's #1 producer of farmed bluefin tuna in the global luxury seafood segment. At the auction floor, each bluefin tuna is assigned an identification number to precisely trace its origin, weight, and fishing vessel. The fish are then moved into a deep-chilled auction hall, where seasoned traders assess quality solely by meat color, fat marbling, and firmness before placing bids through subtle hand signals. The highest record ever set was a bluefin tuna sold for 333.6 million yen, approximately $3.1 million USD in Tokyo. Once the auction concludes and the fish belongs to the winning buyer, master tuna cutters immediately begin breaking down the fish the same night, separating each cut with absolute precision to preserve freshness, texture, and maximum value. Leaving behind the heart-pounding auctions at the harbor, we return to land to encounter Japan's culinary national treasure, Wagyu beef, a type of meat known for its painting-like marbling and aristocratic care process. The high price of this beef, especially the top-grade A5, stems from a feeding cycle that lasts twice as long as industrial cattle. It takes at least 30 months to reach full maturity in marbling structure. Throughout this period, the cattle's diet is fully personalized, consisting of a nutrient-rich blend of grains, rice straw, and soybean pulp. Notably, to prevent stress, an element that can toughen meat and reduce fat quality, farmers raise the cattle in an environment of absolute calm. At some traditional Wagyu farms, particularly during summer, farmers give cattle small amounts of beer to stimulate appetite. Alongside this, manual massage is used as a stress reduction method, helping fat distribute more evenly within the muscle fibers. A cow is allowed to leave the farm only when it reaches 700 to 800 kilograms and passes one of the strictest grading systems in the world. Only meat with a perfect fat-to-lean ratio, vivid red color, and glossy texture earns the A5 stamp. Wagyu fat melts at around 25 degrees Celsius, lower than human body temperature, creating the sensation of meat melting on the tongue with a delicate aroma. Each cow has its own birth certificate, with a unique nose print to trace its lineage, and the most expensive cuts, such as ribeye and tenderloin, are served at luxury teppanyaki restaurants or exported to the United States and Europe at prices of $500 to $1,000 per kilogram, making Wagyu a true symbol of Japanese luxury. There was a time when every Israeli child grew up memorizing one rule: turn off the tap while soaping. A habit that became almost a survival instinct in a land where natural fresh water accounts for less than 1% of the territory. Israel is not the hottest place in the Middle East, but it is among the harshest, hot, arid, and chronically short of water year-round. Trapped between the massive furnaces of the Sahara Desert and the Arabian Peninsula, the country endures brutal climatic disparity. While the north still receives seasonal rainfall, precipitation dropped sharply toward the south, falling below 25 millimeters per year, equivalent to just a 30-minute rain shower in a temperate climate. Moreover, scarcity exists not only in the skies but also beneath their feet. Israel has almost no inland rivers large enough to sustain agriculture. Its only lifelines lie deep within coastal, highland, and Negev desert aquifers, finite treasures that risk saltwater intrusion if overexploited. For this reason, Israel could not survive without creating its own solutions. Beginning in the 20th century, instead of praying for rain, the nation chose to turn scarcity into a strategic advantage, actively producing water through technologies unlike anything the world had seen before. To supplement its water supply, Israel chose an exceptionally smart approach: desalinating Mediterranean seawater. With a long coastline, stable salinity, and minimal exposure to natural disasters, these waters allow mega-scale plants to operate 24/7, regardless of weather conditions. The key lies in reverse osmosis technology. Seawater is forced through ultrafine semi-permeable membranes under extremely high pressure, allowing pure water molecules to pass through, while salts and impurities are retained, producing water that meets domestic consumption standards. What truly sets this technology apart, however, is not filtration alone, but energy recovery systems. By harnessing residual pressure from the concentrated brine stream to compress incoming seawater, Israel has reduced electricity consumption by up to 40%. As a result, production costs have fallen to a record low, less than $1 per cubic meter, among the lowest in the world. The outcome is striking. Around 80% of Israel's domestic water supply now comes from the sea, virtually eliminating dependence on natural rainfall. However, desalinated water is extremely expensive to produce and transport, so it is prioritized primarily for domestic use. To sustain large-scale agriculture in the desert without draining the national budget, Israel activated an often overlooked resource: urban wastewater. This solution has propelled Israel to the global lead, with up to 90% of its wastewater reused, 3 times the rate of the United States. At megascale treatment plants, wastewater containing organic pollutants and microorganisms is fed into massive aeration tanks. Here, bacteria act as natural decomposers, consuming and breaking down harmful organic compounds, transforming dark, contaminated flows into basic clean water. Next, pressure filtration systems and centrifuges completely remove solid impurities and sludge from the stream. This closed-loop process ensures that not even the smallest debris escapes, preparing the water for the most critical purification stage beneath the ground. The water is then directed to desert reservoirs for soil aquifer treatment, the most crucial step in the water regeneration chain. It slowly percolates through sand layers, reaching depths of up to 100 meters, using the earth itself as a vast biological filter to fully eliminate bacteria and remaining contaminants. From this point, the regenerated water reaches a purity comparable to drinking water, sustaining over 60% of agricultural land in the Negev desert at a cost only 1/3 that of desalinated water. But water alone is not enough. For centuries, drawing water from wells was one of the most backbreaking tasks in arid regions. Jewish settlers in the Negev and the Jordan Valley were forced to haul bucket after bucket up from the ground, then carry heavy canisters on their shoulders to irrigate their fields. Water was scarce, labor was intense, and most of that effort simply evaporated under the desert sun. Today, more than 90% of Israel's cultivated land has been transformed by drip irrigation technology. While Israel did not invent the principle, it was the first country to commercialize it and turn it into a fully integrated, large-scale system, operating reliably across open fields and sealed greenhouses alike. After passing through filtration units, water is pushed into main pipelines and then distributed into smaller lateral lines running parallel along planting rows. Along each line, drip emitters are placed 40 to 60 centimeters apart, precisely where root activity is strongest. So water does not spread wastefully but is delivered exactly where plants actually need it. Unlike flood irrigation or overhead spraying, drip irrigation fundamentally solves the long-standing inefficiencies of manual watering. Pressure-regulating valves and automated controllers allow farmers to precisely control flow rates and timing, delivering water steadily into the root zone. As a result, leaves remain dry, soil surfaces are left undisturbed, and most importantly, water loss through evaporation is nearly eliminated. In mushroom farms, where thousands of delicate caps have no roots to draw water, drip irrigation becomes a tool for controlling life itself. Water is supplied in ultra-small doses, slowly absorbed, just enough to maintain optimal humidity for mycelium growth. Here, drip irrigation is no longer about watering, it is precision management of the microbial environment. And now, welcome to the Jordan Valley, the lowest place on Earth, and also the most unforgiving heat basin in Israel. Here, where temperatures of 45 degrees Celsius can scorch nearly all life, and salt-crusted soil gleams white like snow, conditions long considered a death sentence for crops become an absolute advantage for date palms. The medjool date, often called the black gold of the desert, is the star of this landscape. Extreme heat triggers intense sugar accumulation, while soil salinity naturally eliminates pests, allowing the dates to grow completely clean, without chemical intervention. However, producing export-grade dates with near-perfect uniformity requires deep technical intervention. Each mature date palm needs around 700 liters of water per day at the peak of summer. This massive volume is drawn from the Jordan River and delivered through intelligent drip irrigation systems, directing each drop precisely to the root zone, sustaining life without increasing soil moisture, a critical factor in preventing fungal growth on the fruit. From August to October, as harvest season begins, date clusters do not ripen uniformly and are therefore monitored closely day by day, cut only at the exact moment when sugar content reaches its peak. Harvesting is assisted by specialized hydraulic lifting platforms, allowing workers to reach individual fruit bunches at heights of up to 20 meters. Each cluster is cut by hand, then slowly lowered using pulley systems to prevent impact or surface damage. The moment the dates leave the canopy, the clock starts ticking. Within a 6-hour golden window, they must enter processing facilities for controlled cooling and drying. This critical step locks in the fruit's flesh structure and its concentrated sweetness. Few realize that while medjool dates can be grown in many regions, Only in Israel do they reach such exceptional size, richness, and a soft, toffee-like texture that the world relentlessly pursues. Once a luxury tribute offered to Roman emperors, medjool dates today generate up to 350 million USD annually. With an average yield of 120 kilograms per tree, double the productivity of California, America's date capital, this stands as the clearest proof of Israel's mastery over precise water control, ripening timing, and sugar accumulation rhythms, something even temperate climates have yet to achieve. A naturally grown cherry tomato plant. Moving beyond greenhouses, Israel is bringing artificial intelligence into open fields with autonomous apple harvesting robots. As global labor shortages intensify, these robotic fleets are gradually replacing human workers during harvest season. Equipped with computer vision, the robots scan entire canopies, assess ripeness and size, and detect even the smallest blemishes on apples while they are still on the tree. Once a fruit meets the standard, it is picked using vacuum suction grippers or soft clamps, ensuring zero surface damage. The true breakthrough lies in 24/7 operation. These robots can work through the night under specialized LED lighting, enabling rapid harvests ahead of unpredictable weather. The result, up to a 50% reduction in labor costs, while simultaneously upgrading fruit quality. This is how Israel transforms traditional apple orchards into intelligent production lines, as precise and efficient as a high-tech manufacturing plant. We step into winter rose gardens, where even in the harshest cold, technology forces blooms to open on schedule, turning fragile petals into 10 million USD in revenue every single day, a feat possible only in modern agriculture. Winter does not put roses to sleep. Instead, it becomes the season that determines the value of the entire industry. As outdoor supply dwindles, greenhouses turn into arenas of technological competition, keeping roses blooming precisely on demand. Inside these sealed greenhouse structures, technology operates like a living brain. Sensor networks silently monitor every growth parameter, while drones skim just above the plants, spraying nutrients with milliliter-level precision. When buds reach the ideal commercial bloom stage of 70 to 80%, workers immediately cut each stem using specialized shears, executing firm, precise motions to avoid bruising the stem or damaging the petals. Within just 30 minutes, the bouquets are rapidly chilled to 2 to 4 degrees Celsius, slowing plant respiration and preserving freshness. From there, each rose quietly enters the global supply chain, blooming at exactly the right moment in the hands of millions of women across continents. In contrast, winter roses grown outdoors follow a completely different path. With no sensors or machines, harvesting is done entirely by hand, an art that demands absolute precision. When the fragrance reaches its peak, workers move through the cold morning mist, separating each petal according to the flower's natural blooming order. Thousands of blossoms are required to produce just 1 kilogram of fresh petals, a precious raw material that is distilled the very same day. Here, beauty is no longer measured by appearance, but by pure scent, the very soul of the world's most luxurious perfumes and cosmetic creations. Leaving behind the winter rose gardens of Florida, we now turn to Japan, where persimmon orchards enter a short but explosive winter harvest season, generating more than 300 million USD in revenue in just a few weeks. In October, as entire orchards shift into vivid shades of orange and red, the golden harvest season officially begins. During this window, each persimmon variety demands a distinct harvesting method. For thick-skinned, low-canopy varieties, growers spread soft mats beneath the trees and gently shake the branches, allowing the fruit to fall safely without impact damage. In contrast, fully ripe, thin-skinned persimmons must be picked entirely by hand, one fruit at a time, to preserve their smooth, taut skin. For ancient persimmon trees, reaching 6 to 7 meters in height, workers climb ladders or the branches themselves, using long-handled shears to cut each fruit with precision and safety. Immediately afterward, the persimmons are carefully sorted either on-site or within the same day. Soft, sweet fruit is sent directly to market for fresh consumption, while more astringent persimmons are transferred to processing facilities to be made into air-dried hoshigaki. A single persimmon can be priced at up to 50 USD, but behind that value lies an entire chain of manual labor, strict selection, and refined processing techniques, all unfolding in the harsh winter season, where even the smallest mistake can cost an entire harvest. In the final days of the year, while much of the world is bringing the agricultural season to a close, a new journey begins in Yamagata Prefecture, Japan. The journey of apples sleeping beneath the snow. Here, tens of thousands of premium Fuji apples are harvested entirely by hand, then transported to snow-covered mountain regions. Instead of being stored in conventional artificial cold facilities, these apples are buried deep in natural snow, forming a one-of-a-kind biological cold cellar. With stable temperatures hovering around 0 degrees Celsius and high humidity provided by the snow, the apples continue to mature in silence, converting starch into sugar, retaining their crispness, and developing a clean, delicate sweetness found only in Yuki-Ringo, Japan's snow apples. By late March, when the snow begins to melt, each crate of apples is carefully unearthed. Production is extremely limited. It takes thousands of apples to select a single export-grade batch, which allows snow apples to command prices 3 to 5 times higher than ordinary apples. Japanese snow apples, Yuki-Ringo, are not merely a premium agricultural product, but a symbol of a farming tradition defined by precision, patience, and deep respect for nature. In ancient Egypt, the sugar factory of winter, sugar beets are the silent backbone of the temperate sugar industry, contributing nearly 20% of global sugar production. Sugar beets are typically harvested when temperatures hover around 0 to 5 degrees Celsius, a unique window when most other crops have already finished their growing season. As a result, the sugar beet harvest unfolds in the cold, when fields are largely absent of ordinary agricultural activity. When the harvesting machines enter the fields, the entire process is organized like a continuous production line. First, high-speed rotating blades at the front cut away the green tops, clearing the field surface for the lifting stage. Next, the lifting system descends to a precisely calibrated depth, separating the beets from the heavy soil and raising them with evenly distributed force to minimize surface damage. The beets are then carried onto vibrating conveyor belts, where soil, stones, and excess roots are shaken off step by step. The cleaned beets continue through multiple conveyor levels before dropping into a large onboard storage hopper. Once the hopper is full, conveyor systems unload the beets onto waiting trucks along the field edges, transporting them directly to processing plants. Throughout this short but intense harvest season, machinery, transport trucks, and sugar factories operate around the clock to ensure the entire crop is processed in time. Considered a new spearhead of winter agriculture, celery has established its position thanks to stable yields, high harvest value, and consistently strong market demand. The harvest season typically runs from November to February, when daytime temperatures ranged between 5 to 10 degrees Celsius, ideal conditions for celery stalks to become crisp, firm, and well-preserved after harvest. In the fields, human labor remains an irreplaceable first link in the process. Workers bend close to the rows, cutting each plant cleanly at the base with swift, precise motions to keep the stalk straight and the leaves intact. Just seconds later, the celery is placed onto mobile conveyor belts running alongside the field, marking the moment when manual labor hands over to mechanization. From there, machinery accelerates the entire operation. Horizontal blades cut in uniform passes, while rotating knife systems precisely separate leaves from stalks. Every movement flows seamlessly, forming a production line stretched across the open field. Harvesting machines solve the challenges of speed and labor intensity, but their efficiency depends on tightly controlled parameters, since even minor deviations in speed or pressure can bruise and damage the celery stalks. From human hands to precision mechanics, the entire field operates like a winter machine. Rhythmic, efficient, and calculated down to the finest detail. Leaving behind the lush green celery fields, we turn into vast cabbage farms, where these nutrient reserves of the cold season are being harvested at remarkable speed thanks to the arrival of massive machines. Once the machine enters the field, the rhythm of manual labor is replaced by a seamless mechanized process. Hydraulic cutting blades at the front operate swiftly and decisively, cleanly slicing each cabbage in a single precise motion. Immediately afterward, conveyor belts continuously lift the heads, while automated systems remove old and dirty outer leaves along the way, performing preliminary cleaning before collection. As a result, cabbages move straight from the field into storage bins with minimal human intervention. Each machine can harvest 8 to 12 tons per hour, dozens of times faster than manual labor. Equipped with sensors, anti-sinking systems, and self-leveling mechanisms, the harvester moves steadily across soft ground, transforming the entire field into a precise and highly efficient industrial harvesting line. Did you know that there was a time when cinnamon was not considered a spice at all, but a luxury on par with ivory, reserved exclusively for royalty and the elite? The most astonishing part is that at certain points in history, 1 kilogram of cinnamon was worth several months' wages for a laborer, simply because Europeans at the time had no idea where it actually came from. The tropical forests of South and Southeast Asia, including Sri Lanka, India, Vietnam, and Indonesia, are the regions that today still supply over 90% of the world's cinnamon production. For thousands of years, the true origin of cinnamon was deliberately concealed to preserve trade monopolies, and it was this very mystery that pushed humans out to sea, fueling long-distance voyages and the creation of transcontinental trade routes. In the cinnamon industry, things may look similar at first glance, but in reality there are two fundamentally different harvesting approaches, corresponding to two types of cinnamon and two very distinct end uses. With cassia cinnamon, the type most commonly used for ground cinnamon, the harvesting process is optimized for speed and volume. The tree is cut down once the trunk has fully matured, typically after 10 to 15 years of growth, and the worker then prees and strips the thick bark directly from the wood. Every step is aimed at a single goal: extracting as much bark as possible, as quickly as possible, to supply large-scale industrial production. The result is bark that is thick, hard, and aggressively aromatic, while the tree itself reaches the end of its productive life after just one harvest. But the story doesn't end there. Premium Ceylon cinnamon follows an entirely different logic. Ceylon cinnamon trees are slender, grown in clumps, and harvested while still young. Instead of cutting the tree down completely, the stems are cut at the base using a regenerative, coppicing method, allowing the root system to remain alive and send up new shoots. This is where the real difference begins to show. Thanks to this careful approach, a single Ceylon cinnamon rootstock can be harvested multiple times each year, with a productive lifespan of up to 40 years. The reward for that patience is exceptionally thin cinnamon quills, naturally rolling into dozens of delicate layers, releasing an aroma that is light, sweet, and clean, never harsh or overpowering. In simple terms, cassia delivers impact, while Ceylon delivers depth. And it is precisely this depth, something that cannot be rushed or mass-produced, that makes Ceylon cinnamon a true premium spice, small in size but high in value. Once delivered to the processing facility, the cinnamon branches are soaked in water tanks for at least 15 minutes to soften the fiber structure, remove surface impurities, and stabilize moisture levels. Once the cinnamon stems are ready, the moment that truly determines their value begins. The bark scraping stage is not just a processing step, but the clear dividing line between premium cinnamon and low-grade cinnamon, arguably more critical than cultivation or drying. The worker holds a specialized scraping knife with a short, curved blade sharpened at a very narrow angle, guiding the hand with millimeter-level precision, so the blade glides over the fragile inner bark, rather than chopping or cutting downward. This inner layer is typically only about 0.2 millimeters thick, so delicate that even a split second of excessive pressure will tear the bark and destroy its commercial value. After scraping, the thin cinnamon bark layers are processed immediately while still wet and stacked around a central core of bark to form a cinnamon quill. The reason is simple. Each layer is only a few tenths of a millimeter thick, far too thin to hold its structure once dry. The worker selects bark strips with similar moisture levels and stacks them in an overlapping pattern along the grain to distribute shrinkage evenly. Typically, 8 to 12 layers are assembled, just enough to reach a standard thickness of about 3 millimeters, while creating a hollow structure that helps retain and lock in essential oils. Thanks to this technique, the cinnamon quill naturally curls as it dries, forming an even, lightweight, yet sturdy tube. If this step is skipped or done incorrectly, the bark will warp, crack easily, and is almost impossible to turn into premium cinnamon sticks. After being stacked, the cinnamon sticks enter a controlled drying stage. Instead of being exposed to direct, harsh sunlight, they are placed on multi-tier drying racks indoors or under covered shelters, where light is diffused and air circulates evenly. This process typically lasts around 7 days, depending on weather conditions. The goal is not to dry the cinnamon completely, but to reduce moisture content to about 10 to 12%, dry enough for storage while still preserving essential oils. During this period, the bark layers shrink slowly along the grain, causing the sticks to naturally curl into tubes. If drying happens too quickly, essential oils evaporate. If too slowly, the cinnamon can mold or warp. When done correctly, the cinnamon reaches a stable state and can be shipped thousands of kilometers by sea, while retaining its original aroma. Once drying reaches the required standard, the cinnamon is graded based on length, degree of curl, and the radius of each quill, key factors that determine the commercial value of every stick. After grading, the cinnamon enters the cutting stage, where the agricultural product begins to be standardized into a commercial commodity. Bundles of cinnamon are aligned and cut into standard lengths, typically ranging from 5 to 20 centimeters. Longer pieces are packaged in bulk for wholesale, while sticks shorter than 3 inches are distributed to the retail market. This stage demands decisive yet precise handling, as even a slightly misaligned cut can cause the thin bark layers to separate, making the stick lose its shape and drop in grade. Because of this strict requirement, cutting productivity remains limited. Each worker processes only a few dozen bundles per hour. In return, the finished cinnamon achieves uniform sizing and is fully prepared for packaging, shipping, and global export. After grading, a portion of the cinnamon is directed into the grinding process. Before grinding, the cinnamon is not processed immediately. Instead, its moisture content is checked and stabilized below 12% to prevent mold and ensure that essential oils are not altered during subsequent steps. Once this condition is met, the cinnamon enters a closed grinding system. The sticks are gradually broken down, passing through multiple stages of blades and rollers in an environment where the temperature is kept consistently below 40 degrees Celsius. Maintaining low heat is critical, because once cinnamon is ground into powder, its surface area increases dramatically, making essential oils far more prone to evaporation than in whole sticks. For this reason, freshly ground cinnamon powder is not left exposed. It is immediately sifted to remove coarse particles, brought to a uniform fineness, and then packaged and sealed right away. Leaving behind the cinnamon factories, where the warm, spicy aroma still lingers in the air, the next stop on our journey is Indonesia, a tropical nation with a hot, humid climate, fertile volcanic soils, and vast archipelagos stretching along the equator. These natural conditions are nearly ideal for nutmeg cultivation. Today, Indonesia accounts for around 60% of global nutmeg production, making it the most important center of this spice, often referred to as the fiery jewel of the spice world. Nutmeg is one of the very few spices whose harvest timing is determined entirely by the fruit itself. When fully ripe, the outer husk naturally splits open, revealing the nutmeg seed and the bright red, web-like aril wrapped around its core, the only signal that harvesting is allowed. Nutmeg trees can grow up to 15 meters tall, far beyond human reach. When the fruit reaches full ripeness, farmers use long poles fitted with a sickle blade at the tip to hook and pull the stem, causing the fruit to fall to the ground, where it is then quickly collected. Crucially, The harvest window for each fruit lasts only about 24 to 48 hours from the moment the husk begins to split. Any delay beyond that causes quality to decline rapidly. The pressure intensifies during the rainy season, when growers must inspect every tree daily, navigating slick trunks and constant threats from red ants and fire ants. With nutmeg, precision is not an advantage, it is a requirement for survival. After harvesting, the nutmeg fruits are gathered and thoroughly washed to remove soil, sap, and insects clinging to the surface. This seemingly simple step helps reduce the risk of fungal contamination from the outset and prepares the fruit for precise shelling in the subsequent stages. Once cleaned, the nutmeg is completely shelled by hand to extract its most important core, the nutmeg seed. This is the part that contains the highest concentration of essential oils, responsible for the spice's warm, pungent aroma and the depth of its flavor. During this process, the worker must also carefully remove the red aril, known as mace, a delicate, web-like layer that clings tightly to the seed. Mace is a spice in its own right and highly valued, but its fragility makes the task extremely difficult. A momentary lapse in pressure can tear the mace and easily damage the seed beneath. A small crack in the seed can reduce its commercial value by 40%, even though its outward appearance may remain almost unchanged. An intact nutmeg seed can retain its aroma for up to 4 years, while a scratched or damaged seed can lose its fragrance within just a few months. After separation, the two parts of nutmeg follow two different paths. The red aril, or mace, is shade-dried in well-ventilated conditions for several days to preserve its color and aroma. Meanwhile, the nutmeg seeds must be air-dried or gently dried for 4 to 8 weeks, until their moisture content drops to a safe level. During this time, the hard shell naturally cracks open and the essential oils fully stabilize. Once the nutmeg seeds meet quality standards, they are gathered and given a final cleaning before entering the stage that ultimately defines their aroma, grinding. Unlike many other spices, nutmeg allows virtually no margin for error. Once temperatures rise above 45 degrees Celsius, key aromatic compounds begin to evaporate rapidly, causing the seeds to lose their fragrance even before they become powder. For this reason, the entire grinding process takes place in a sealed, temperature-controlled environment where speed is deliberately sacrificed in favor of preserving aroma. The seeds are ground through multiple stages until they reach a particle size of just 50 to 70 microns, finer than premium wheat flour, allowing the aroma to disperse evenly from the very first use. The powder is then sieved, quality checked, and hermetically sealed to lock in essential oils and extend its aromatic lifespan. At this point, the journey of nutmeg is nearly complete. From a small fruit in the tropical forest to a refined spice capable of retaining its aroma for years, ready to appear in kitchens anywhere in the world. Known as the second most expensive spice in the world, after saffron, vanilla was once valued at the equivalent of a gold bar per kilogram. Yet vanilla is not merely a spice with an astonishing price tag, it is also a strategic ingredient underpinning the entire global industry of confectionery, beverages, and premium foods. With vanilla, harvesting is not simply about picking pods. It is a harsh race against time, humidity, and even other people. Its high value makes vanilla a constant target for theft, forcing many farms to accept the reality that around 10% of their annual yield disappears each year before the pods ever leave the field. Vanilla reaches peak quality only within a very narrow window of ripeness. Harvesting too early results in weak aroma, while being late by even a single day in humid conditions can cause mold and reduce the pod's value by up to half. For this reason, each vanilla pod is cut entirely by hand using a small knife, requiring speed paired with absolute precision, and is then immediately gathered and transported within the same day to prevent any uncontrolled fermentation from beginning. When the vanilla sacks arrive at the processing facility, they immediately enter a strict security control system. The entire site is surrounded by barbed wire fencing and monitored 24/7 by surveillance cameras to prevent theft. In their raw state, vanilla pods are hard, brittle, and almost entirely odorless. To awaken the latent aroma inside, the pods must undergo a hot water blanching step. This brief but precisely controlled heat treatment softens the pod structure while simultaneously halting natural growth. More importantly, it triggers a chain of enzymatic reactions within the pods, initiating the formation of the characteristic aromatic compounds. Among these compounds, vanillin is the dominant component, accounting for around 90% of vanilla's signature flavor profile. After blanching, the vanilla pods enter the sweating stage, during which they begin to turn a deep brown. This process reduces moisture, concentrates flavor, and allows vanilla's characteristic sweetness to develop. While still warm, the pods are placed into wooden boxes lined with multiple layers of blankets to retain heat for as long as possible. The boxes are then sealed for 48 hours. By the end of this stage, the pods have darkened significantly and are ready to move on to the drying phase. The drying process of vanilla takes place in two stages: sun drying and shade drying. This step is crucial for allowing the pods to fully develop their aroma and rich color. The vanilla pods are spread evenly on cloth and exposed to sunlight for 3 to 5 hours per day over many consecutive days, and are turned frequently to ensure even drying. During this process, skilled workers gently massage the pods to help release essential oils and intensify the aroma. However, the pods cannot be left in the sun all day, as vanilla must retain a certain level of moisture for its flavor to continue developing. After sun drying, the pods are covered and stored overnight, then returned to the sun the following day. After approximately 10 to 15 days of sun drying, the vanilla pods are moved to shade drying in a well-ventilated environment, where they remain for 2 months. After the drying process is complete, vanilla pods undergo strict grading based on length, flexibility, color, and aroma. Pods that meet quality standards are bundled into small groups and tied with twine to preserve their natural shape and prevent cracking during transport. However, not all dried vanilla carries the same value. Across total production, only about 20 to 30% of the highest quality pods are selected for refinement into natural vanilla extract, the most economically valuable product in the vanilla processing chain. The remaining pods are typically sold as dried whole vanilla or used for lower-grade flavoring applications. More striking still, in a global market with enormous demand for vanilla, around 95% of products labeled vanilla contain no real vanilla at all, relying instead on synthetic flavorings. This reality makes each properly cured natural vanilla pod not only rare, but a true concentration of time, craftsmanship, and months of patience. Introduced in the 1950s, born from the need to create a cheese slice that was more stable and easier to store than traditional cheeses, Kraft singles today are found almost everywhere, from burger counters and industrial kitchens to global fast food chains, with billions of slices produced and consumed each year. More visually appealing than cheddar when melted, more resilient than fresh mozzarella, yet not legally considered real cheese, this product is in fact a processed cheese, containing only about 51% real cheese. The rest is water, emulsifying salts, and technical ingredients designed to control structure and melting behavior. With overwhelming popularity in the processed cheese slice segment, Kraft singles are estimated to generate around USD 1.5 billion in profit annually for Kraft Heinz, enough to place the product among the company's crown jewels, alongside global icons such as Heinz Ketchup, Kraft Mac and Cheese, and Velveeta. To create a perfectly melting Kraft single slice, everything begins with ingredient selection, where base cheese blocks such as cheddar, Colby, and other semi-hard cheeses are carefully chosen. Once the ingredients meet the required standards, the cheese blocks are transferred onto the processing conveyor and enter the grinding stage, where the breakdown of structure is controlled down to the finest detail. At this stage, the cheese blocks must be kept in a solid state to prevent phase separation of fat and protein prior to emulsification. Industrial blades rotate continuously to break the cheese blocks into smaller pieces, increasing surface area and preparing the material for the subsequent emulsification cooking step. At the same time, Air becomes the invisible enemy of the entire process. If oxygen is drawn in during grinding, it can trigger oxidation reactions, altering flavor and disrupting the color that must remain stable. For this reason, the grinding system is designed to be nearly fully enclosed, minimizing air intrusion and keeping the cheese in an absolutely stable state before it moves on to the next stage. With traditional cheese, shelf life after opening typically lasts only 5 to 7 days. In contrast, craft singles can remain stable for 30 to 60 days in the refrigerator. This difference does not come from magic, but from the step where emulsifying salts and water are added, and the mixture is cooked in a continuous system for just a few minutes. Here, the cheese transitions from a solid, separated, and difficult-to-control state into a molten form, ready to be shaped and transformed into millions of craft singles slices. After melting, the cheese is poured into molds, where it solidifies again under controlled temperature and pressure, forming uniform blocks ready for the cutting stage. From these formed blocks, the processed cheese is sliced into standard pieces of approximately 9 × 9 centimeters, only a few millimeters thick, using high-speed cutting systems operating continuously. Immediately after cutting, each cheese slice is wrapped in a thin film to secure its shape, then sent directly through a controlled cooling water bath. The cold water rapidly lowers the temperature, locking in thickness and cut edges before the slice has a chance to spread or warp, while also bringing the temperature down to a safe range so the subsequent wrapping process can proceed smoothly. The entire cycle is completed in approximately 30 seconds, using a circulated water system that is sterilized and closely monitored, ensuring that each slice retains its structure without absorbing water. This practice of individually wrapping each slice during the cooling stage is a distinctive feature of Kraft's production line. Rather than allowing the cheese to fully stabilize before packaging, Kraft fixes the shape and state of each slice within the thermal process itself, ensuring high uniformity, easy separation, and consistent quality in use, an approach that is critical for large-scale industrial production. After the cooling stage, the slices are transferred directly to the automated packaging area, where pick-and-place robots handle the entire operation. Mechanical arms move along precisely repeated paths, lifting each slice, placing it into trays, and aligning positions before sealing, at speeds that can exceed 200 slices per minute. Human workers only supervise and perform random inspections, while consistency, hygiene, and production pace are entrusted entirely to machines, fast, precise, and tireless. Farewell to Kraft singles and the familiar rich, creamy cheese slices. Up next, we turn to butter, the strategic pillar of the global dairy industry. To produce butter, everything begins with fresh milk, a familiar raw material that is strictly controlled from the very first moment. When tanker trucks arrive at the plant, the milk is pumped directly into stainless steel silos within a closed system, with minimal exposure to air. Temperature is kept stable from farm to factory to prevent oxidation and bacterial growth. Before entering production, the milk must pass a series of tests: fat content, pH, microbiological levels, antibiotic residues, and impurities. A single deviation is enough for an entire truckload to be rejected, because in butter production, quality always takes precedence over yield. Milk that has met quality standards is gently warmed and fed into a centrifugal cream separator. At speeds exceeding 7,000 revolutions per minute, the lighter fat fraction is separated as cream, while the remainder becomes skim milk. The cream remains liquid, fat-rich, and serves as the core ingredient for subsequent churning and butter production. After being pasteurized at approximately 85 to 90 degrees Celsius for a short period and aged at 5 to 10 degrees Celsius for several hours, the cream remains in liquid form and is transferred directly into an industrial butter churn, where the transformation truly begins. Under continuous agitation, the fat structure breaks down. The cream gradually thickens, then small butter grains appear and aggregate together. The liquid separated during this process is buttermilk, commonly used in food processing, while the butter in granular form is collected and prepared for the subsequent processing stages. Immediately afterward, the butter mass is washed with cold water at 5 to 10 degrees Celsius to remove nearly all remaining buttermilk. a critical step that determines the product's shelf stability. If buttermilk is not thoroughly removed, the butter can turn sour within just a few days. When properly handled, however, the butter can maintain its quality for many months. Next, the washed butter is transferred to specialized working machines. Through controlled pressing, folding, and mixing, the butter gradually transitions from a loose, non-uniform granular state into a cohesive, smooth, and pliable mass, with moisture evenly distributed throughout. At this stage, the butter reaches a fat content of 80 to 82%, meeting global commercial standards. Finally, the butter is formed into small retail blocks or large units of 20 to 25 kilograms, and even 200 to 500 kilograms for industrial kitchens. Batches of butter weighing more than an automobile. Just minutes later, the butter enters the most demanding area of the factory, the packaging zone, where temperatures are constantly maintained at 10 to 15 degrees Celsius, nearly as cold as a meat storage facility. Here, speed is no longer an advantage but a matter of survival. If the line runs 3 to 5 seconds slower than designed, friction and ambient heat alone are enough to soften the butter's surface and cause deformation before sealing can occur. Packaging, therefore, serves more than a protective outer layer. The factory uses multi-layer materials coated with polymer or thin aluminum to block light and foreign odors. Even a minor deviation can cause the butter to lose its aroma and decline in quality within just a few weeks. Before shipment, the butter undergoes final quality checks on packaging integrity, weight, shape, and sample analysis to ensure compliance with standards. If Chinese people cannot live without chili oil, Americans can hardly enjoy bread without peanut butter. Each year, the United States consumes approximately 152,000 metric tons of peanut butter, averaging about 2 kilograms per person, generating a multi-billion-dollar market annually. The first step in peanut butter production is washing the peanuts, where dirt and impurities are removed and underweight or damaged kernels are separated. Only peanuts meeting structural and weight standards proceed to the next stages. The first step in peanut butter production is washing the peanuts, where dirt and impurities are removed and underweight or damaged kernels are separated. Only peanuts meeting structural and weight standards proceed to the next stages. After roasting, the peanuts are immediately transferred to a critical refining stage, skin removal, a step that directly determines the color and flavor of the final peanut butter. Here, the kernels pass through a modern skin removal system, where compressed air at 6 to 8 bar, combined with ultrafine grooved rollers, strips away the thin skins without breaking the kernels. Even a small amount of residual skin can introduce slight bitterness and darken the color, noticeably affecting smoothness and richness. Next, the peanuts move along a vibrating conveyor with high-power suction fans to remove any remaining skin fragments. This process also cools the kernels naturally, preventing overcooking before grinding. Before milling, the peanuts pass through an optical sorting system. High-speed cameras scan 5,000 to 7,000 kernels per minute, detecting burnt, discolored kernels or foreign matter, and ejecting them instantly using compressed air. When peanuts enter the rotary grinding system, high-speed shear and friction release natural oils, forming a smooth, golden paste without dairy ingredients. Heat from grinding improves flow before stabilization. Salt, small amounts of sugar, or vegetable oil are then added in precise proportions to refine flavor. The mixture is heated to about 180 degrees Fahrenheit to stabilize structure, reduce bacteria, and extend shelf life, with low moisture and high oil content, minimizing the need for preservatives. At the final stage, the peanut butter is kept at a stable warm temperature and transferred directly into an automated packaging line, where controlled heat allows the product to flow smoothly without foaming, while maintaining filling accuracy with deviations of only a few grams per jar. The peanut butter is then dispensed into glass or plastic containers ranging from 250 grams to 1 kilogram and sealed immediately. As the temperature gradually drops, a slight vacuum forms inside the container, limiting oxygen intrusion and preserving flavor. Immediately afterward, the product undergoes rapid cooling, labeling, and final inspection before being packed into cartons. The entire process takes place in a fully sterile environment, strictly meeting food safety standards. When it comes to peanut butter on the global market, Skippy stands out as the most recognizable name. Founded in 1933, Skippy built its success on an approachable flavor, consistent texture, and wide international distribution. With annual revenue exceeding $1 billion, Skippy represents both massive economic value and a lasting cultural presence in everyday food habits. Alongside Skippy, the market also features major competitors such as Jif, Peter Pan, and Justin's, which together drive competition and innovation in the peanut butter industry. Hemp isn't a common plant for most Americans, but the truth is there are far more surprising and fascinating things about it than people realize. In the materials industry, hemp is considered one of the few crops that can truly solve the sustainability equation. Producing 1 kilogram of fiber requires only about 1,500 liters of water, while cotton consumes 13 times more, and polyester relies entirely on petroleum and leaves behind microplastics. Not only that, 1 hectare of hemp can absorb 2 to 4 times more CO2 than a tropical rainforest, making it one of the most powerful carbon-capturing machines humans can cultivate. With advantages this obvious, many people wonder, why hasn't hemp grown as strongly as other materials? The answer lies in the very first doubt you probably had when looking at its leaves. For nearly 70 years, cannabis plants were lumped together under narcotics legislation, even though industrial hemp has no psychoactive effect whatsoever. Ironically, cotton, nylon, and paper manufacturers only intensified the stigma through lobbying efforts designed to keep hemp banned and eliminate a far more sustainable competitor. It wasn't until the global shift toward bio-based materials and the United States officially legalized hemp in 2018 that this buried ace card was finally revealed again. Modern fiber processing technology has pushed hemp to a new level. As soft as cotton, as breathable as linen, yet stronger than polyester. Today, global hemp cultivation has surpassed 770,000 hectares, and the hemp fashion market alone is nearing $6 billion, a milestone proving that the era of sustainable materials is no longer a promise, but a reality already gaining momentum. The journey of every hemp plant begins with millions of seeds being sown into the soil each April and May across Colorado, the hemp capital of the United States. With its dry climate, large day-night temperature swings, and an average elevation of over 1,500 meters above sea level, the region offers ideal conditions for fast germination, straight stem growth, and the highest fiber content throughout the plant cycle. Before reaching the fields, the seeds are cleaned, graded, and pre-germinated in trays to ensure uniform quality. Thanks to automated seeders capable of handling around 200,000 seeds per hour, farmers no longer have to plant by hand, cutting labor needs by more than 70% while keeping planting density perfectly calibrated for each production purpose. From there, hemp grows rapidly. In just over a month, the rows close their canopy, covering the field as the plants enter their biomass building stage. Another month later, they shift into reproduction. Leaves widen, small flower clusters appear at the stem tips, a signal that the plant has completed its vegetative growth. The optimal time to harvest hemp is late summer, when more than 6,500 hectares of industrial hemp in the San Luis Valley simultaneously reach ideal height and biological maturity for producing bast fiber and woody hurd. At this stage, specialized harvesters are brought into the fields, machines capable of cutting stalks close to the ground, preserving their full 2.5 to 3.5 meter length, and aligning them in a single direction during operation. This cut and line technique minimizes stem twisting and breakage, reduces bast skin damage, and preserves more than 80% of fiber value right at the field. After cutting, the machine spreads the stalks evenly across the field to ensure a stable retting process. Natural dew retting, driven by moisture and microbial activity. Standard retting takes 2 to 6 weeks, depending on soil humidity, nighttime dew, and temperature fluctuations, all of which affect how quickly the pectin layer bonding the bast and hurd breaks down. By maintaining the integrity and tensile strength of the bast fibers, the proportion of stalks meeting spinning grade quality increases significantly, boosting productivity to over 5 tons of dry stalks per hectare, a level manual labor can hardly achieve at scale. Unlike harvesting hemp for fiber, which requires keeping the stalks long and intact, harvesting hemp for hemp cement, Hempcrete doesn't require taking the whole plant. Instead, growers use forage harvesters or specialized hemp decortication harvesters. These machines operate using a high-speed rotary cutting system at the front, slicing the stalks into short segments as soon as they enter the intake. After that, a hammer mill or chopping drum further processes the stalks, breaking them down into small pieces ranging from 5 to 25 millimeters, the optimal size for separating out the hemp hurd, the lightweight woody core used in construction materials. The shredded material is then carried upward by an auger conveyor directly into the machine's rear collection tank, or transferred into a towed trailer for transport to the decortication facility. And now we've arrived at the most exciting part of today's video, the process of transforming hemp into high-performance, next-generation materials. The production of hempcrete begins with separating the woody core from the outer fiber. After harvesting, the hemp stalks are fed into a decorticator, where counter-rotating rollers and crushing drums mechanically break down the stalk, peeling the bast fibers away from the hurd through compression, shear forces, and continuous oscillation. Immediately afterward, a system of screens and air separators automatically filters out short fibers and impurities, retaining only clean, uniformly sized hurd with its structural integrity intact. After being screened, the hurd is fed into a dry mixer to loosen the fibers and increase aeration before combining with the binder. Immediately afterward, hydraulic lime or hydrated lime is added at the standard ratio of 1 part hurd, 1.5 parts binder, and 2 parts water. This ratio is specifically formulated to allow easy shaping and mineralization while preserving the hurd's natural properties, porosity, lightness, and its inherent ability to regulate moisture. After that, the mixture is placed into molds or an in-situ casting system according to the designed thickness. Each layer is lightly compacted and leveled to achieve moderate density, while still maintaining moisture release and air retention capacity. When it comes to real-world construction, hempcrete is used in 2 main ways. For projects with standardized designs, builders rely on precast blocks and panels. The mix of hemp hurd and binder is molded, dried, and delivered to the site. Workers simply install these units onto the structural frame and wait for them to set, fast, clean, and with consistent quality control. The second method is more flexible and suited for projects that require on-site shaping. Hempcrete is used as a lightweight concrete that can be applied or sprayed directly onto a pre-assembled structural frame. Compared to using precast blocks, casting hempcrete in place creates a seamless, monolithic wall with no joints, resulting in better thermal retention, reduced heat loss, and a clearer expression of hempcrete's natural ability to regulate temperature and humidity. A house built with on-site hempcrete typically takes around 7 or 10 days to dry and set. In return, the walls can withstand over 2 hours of continuous fire exposure, are non-combustible, produce no toxic smoke, and do not weaken structurally. In addition, this material continues to absorb CO2 throughout the building's lifespan, helping the house stay cooler in summer and warmer in winter, a key reason why it has already been adopted in more than 40,000 buildings across Europe and North America. Beyond its role as a bio-based construction material, hemp holds another, far more common potential hidden just beneath its soft outer bark: hemp fiber, a natural fiber that is several times stronger than cotton. After several days to weeks of field retting, the dried hemp stalks are transported to the processing facility, marking the official beginning of their transformation from an agricultural crop into an industrial raw material. At the intake gate, any stalks that are curved, have a moisture content above 18%, or are fractured will be rejected. Immediately afterward, the remaining stalks enter the decorticator, but instead of retaining the woody hurd. This entire process is designed to separate and preserve the long bast fibers, the only component used for fiber production. At the critical stage, the bast fiber bundles enter the carding system, where thousands of steel needles on counter-rotating cylinders continuously disentangle, deep clean, and stretch the material. Each hour, a single production line can perform over 20 million micro-carding actions, generating a level of fiber separating force and precision that no manual tool could ever achieve. With every pass through the machinery, the fibers are straightened, fully separated from herd particles and impurities, and stripped of short, non-standard segments. The result is a stream of smooth, parallelized fiber slivers with stabilized length, officially entering the next stage of high-precision processing. After carding, the sliver is still soft, uneven, and lacks fiber structure, so it is sent through the drawing system. Here, multiple slivers are drafted and combined into a single, uniform strand to equalize density, adjust tension, and stabilize the dimensions of the roving before twisting. Once the sliver is stabilized, it enters the spinning stage, the process that ultimately determines yarn quality. The first step is roving, where the sliver is gently twisted to form a semi-finished strand, strong enough to withstand drafting without breaking. This roving is then transferred to the ring spinning stage, where it is further drawn out, reduced in thickness, and tightly twisted to create the final yarn, meeting industrial standards for tensile strength, fineness, and twist. At modern operating speeds, a single ring spinning machine can produce over 150,000 meters of yarn per hour, transforming loose, disorganized fibers into uniform and stable yarns, ready for the subsequent weaving and dyeing processes. At the end of the production process, the finished fibers are wound into large spools, each stretching from 8 to over 25 kilometers, depending on manufacturing standards. At this stage, hemp fiber is fully processed and technically complete, officially becoming a feedstock for textiles, biocomposites, cellulose engineering, and various forms of industrial reinforcement materials. Leaving the factory, hemp fibers enter supply chains in more than 30 countries, with the fashion industry consuming over half of all output. And although hemp is not yet as mainstream as cotton or polyester, full collections made entirely from hemp fiber have already begun to appear. Few people realize that if somewhere in a landfill, you find a t-shirt that decomposes completely within just 6 to 8 months, there is a good chance it was made from hemp. Even more remarkable, every ton of discarded hemp fiber continues to absorb nearly 2 tons of CO2, creating a net positive environmental impact, rather than contributing to degradation like most other fibers today. For decades, Indonesia, the Philippines, and India have been the undisputed leaders, commanding over 70% of global coconut production. Yet in the arena of byproduct recycling, India stands as the true powerhouse, processing more than 500,000 tons of coir and cocoa peat each year and steering this billion-dollar industry. As the green living movement accelerates worldwide, demand for coir and cocoa peat has surged by 15% annually. What transformed materials once dismissed as agricultural waste into a global phenomenon? It starts with a natural paradox. Coconut fiber is organic, yet as tough as synthetics. Biodegradable, yet slow enough to endure 2 decades before breaking down. Combined with the coconut's near zero waste nature, these traits have turned its byproducts into a genuine green goldmine. On the benefit side, recycling 1 ton of coconut husk can cut up to 250 kilograms of CO2, but left to rot or burned, that same husk releases methane, CH score, a greenhouse gas 28 times more potent than CO2. In a world facing escalating environmental crises, recycling coconuts is not only an ecological rescue but a remarkably smart way to turn waste into a multi-billion-dollar opportunity. Thousands of products are now born from coconuts, from construction materials, carpets and mattresses, to cosmetics and even road surfaces. Hard to believe? And that is exactly why you're here, to begin this remarkable journey of renewal, back to the tropical coconut groves, where every new life of the coconut begins. Coconuts are not exactly a cooperative fruit. They grow in heavy clusters, clinging to the tops of 20 to 25-meter trees, turning every harvest season into something of an adventure sport, where a single unlucky slip could easily cost a picker a few non-replaceable components. If in the past, farmers had to gamble with safety by climbing straight up the tree or using long poles to hack down the bunches, both dangerous and prone to cracking the fruit. Today, they have a far smarter solution. Long harvesting poles, designed for just the right reach and tipped with curved blades that are sharp yet flexible, have become the ultimate tool. One clean sweep from an outstretched arm is enough to send a 30-kilogram cluster crashing down. The transportation method is just as ingenious. Shallow irrigation channels dug between coconut rows act as natural shock absorbers, catching the falling bunches from tens of meters above while preventing almost all surface damage. The coconuts are then gathered directly on the water, tied into floating chains like buoy lines, and towed back to the collection point. And that is only the beginning, because once the fresh coconuts reach the processing plant, their second life truly begins. A peeling journey that reveals the precious 30% inside, while the remaining 70%, that rugged outer armor, is reborn as coconut fiber. Thousands of tons of coconut husks pour into recycling plants, stacked into massive mountains, and left under the sun for several days to reduce moisture and soften naturally before entering their transformation phase. Once they reach the ideal dryness, these seemingly useless shells are fed into industrial shredders, where blades spinning at 1200–2800 RPM relentlessly tear, slice, and break apart the tough outer layer. Thanks to the strong cutting force and multi-tier steel blades, the machines can process tons of material per hour, producing a mix of long fibers and fine cocoa dust. This step is critical. The looseness and uniformity achieved during shredding directly determine the efficiency of subsequent cleaning, drying, and fiber separation stages. Fibers that meet the standard move on to screening systems to remove dust before being sun-dried or heat-dried to reach stable moisture levels. Once complete, the coconut fiber becomes a light, durable, and resilient material, ready to be reborn as mattresses, carpets, growing media, or countless other sustainable bioproducts. After being separated from the outer husk, coconut fiber is spread across large drying yards to soak up natural sunlight, preparing it for the next crucial stage, carding. Here, fast-moving cone rollers separate clumps, stretch the fibers, and align them into smooth strands. The result is a clean, uniform fiber stream, making carding essential for the consistency required in later twisting and weaving steps. After being finely carded, the coconut fiber is transferred to the spinning system. Here the fiber bundles are twisted into small ropes or high-strength yarns, with each rotation tightening the strands and building the durability required for demanding applications. The twisting process binds the fibers firmly together, producing cords that are strong, resilient, and capable of withstanding significant tension. These cords become the core material used for weaving coir mats. Every parameter, twist level, diameter, density, and tensile strength is closely monitored to ensure exceptional consistency, giving the final mats superior longevity, structural stability, and outstanding surface grip. Once the finished coconut fiber yarns are ready, they are fed into large weaving frames to form mats with the required thickness, density, and decorative patterns. In this stage, the warp threads are stretched tightly across the loom, creating a firm backbone for the mat, while the weft threads are passed rhythmically through each gap. Layer by layer, the two systems interlock to build a dense, stable structure that gives coir mats their signature coarse texture and remarkable durability. Every movement of the loom, whether powered by hand or machine, is calibrated to maintain tension, spacing, and uniformity. This precision ensures that the mats remain resistant to wear, maintain excellent grip, and hold their shape even under heavy use. Weaving is the defining step where craftsmanship and mechanical accuracy converge, shaping raw fiber into a finished product. Once the weaving is complete, the mats proceed to trimming, edge reinforcement, surface finishing, and final packing for shipment. In many traditional workshops, coconut fiber ropes are spread evenly across the floor before entering the sheet-forming stage, using a wooden framing tool. This specially crafted frame functions like a hand-driven mechanical mold, with parallel wooden slats set at fixed intervals to guide craftsmen as they pull each strand into place without misalignment. Every lift and drop of the frame applies just enough pressure to lock the fibers in position while forming clean, straight channels across the surface. As the frame moves, workers use wooden mallets to tap rhythmically along the mat, compressing each layer of fiber to create a uniform structure, reduce air gaps, and maintain an even thickness. The process demands a precise understanding of force, rhythm, and fiber tension, skills gained only through years of experience. Through the harmonious combination of delicate craftsmanship and the intelligent design of the wooden frame, the finished coir sheets emerge strong, yet breathable, ready for the next stage of mattress pressing or mat weaving. Yet, the production process does not end there. The light, loose fibers left behind after weaving, too thin and lacking the structural cohesion required for mattresses or mats, are collected separately and routed into an entirely different manufacturing line. Here, this material, often dismissed as mere byproduct, becomes the ideal input for modern thermoforming technology. Golden bundles of fiber are evenly spread across heavy steel molds, forming a precise base layer. When the mold closes, the fibers are subjected to intense pressure, typically between 3 and 8 tons, combined with high heat. Under these conditions, the natural lignin within the coconut husk softens and flows, binding the fibers together from within. This unique mechanism allows the material to take shape without the use of any chemical adhesives, relying solely on the coconut's own organic resin. Only a few seconds later, the mold opens to reveal fully formed biodegradable coir pots. Lightweight, breathable, well-drained, moisture-retentive, and capable of breaking down completely in soil within months. Their naturally interwoven, root-like fiber structure allows plant roots to penetrate the pot walls easily, avoiding the circling and constriction commonly seen in plastic containers. Though these pots cannot match synthetic materials in long-term outdoor durability, they dramatically reduce plastic waste and are increasingly favored by growers and nurseries worldwide. Today, these coir-based containers are exported to more than 40 countries, becoming a small but significant part of the global shift towards sustainable horticulture. The newly formed pots are then moved to the finishing table, where any excess edges are trimmed cleanly to achieve a precise, uniform shape. Each pot undergoes a final inspection for thickness, compression, and surface quality before being packed, completing the coir fiber's transformation into a fully biodegradable product. But the journey of coir doesn't end there. Humble as it has become a key material in sustainable road construction thanks to its elasticity, drainage ability, and strong soil-binding properties. Before the coir layer is installed, the roadbed is cleared, moistened, graded, and compacted to the required density. Once the roadbed has been compacted, large coir sheets are laid evenly across the surface. Workers stretch each sheet along the alignment, overlap the edges, and smooth out the entire layer so it conforms tightly to the terrain. After the sheets are positioned, metal stakes are driven through the edges to secure them in place, creating a natural stabilization layer. No plastic, no waste, and at a cost up to 60% lower, making it ideal for rural roads where budgets are limited. With the sheets anchored, the coir immediately begins to do its job, holding soil in place, reducing surface slippage, limiting edge erosion, and dispersing loads across the subgrade. Though biodegradable and temporary, this very trait makes it a sustainable material that leaves no waste behind once its purpose is fulfilled. Immediately afterward, a truck spreads crushed stone evenly over the coir layer. The stones settle through the fiber mesh and lock into its natural structure, forming an effective mechanical interlock. After the layer of crushed stone is compacted by the roller, workers spread a layer of soil over the surface to fill the gaps and increase the stability of the roadbed. A final pass of the roller then locks the entire structure into place, forming a solid foundation for the layers that follow. Finally, asphalt is laid over the compacted base, completing the road surface with a durable, weather-resistant finish. From coarse fibers on tropical farms to mats, mattresses, plant pots, and even sustainable roads, coconut coir is now woven into everyday life around the world. Each year, the coir and cocoa peat industry alone generates more than $4 billion for producing countries, transforming what was once dismissed as agricultural waste into a true green gold mine. And this journey is far from over. As the world accelerates towards sustainable living, the future of coir will only grow broader, brighter, and more promising. If China is the world's pork production engine, then the United States is the king of consumption, a place where bacon, ham, and pepperoni never go out of style. Despite warnings about colorectal cancer risks, estimates show that by 2025, Americans consumed around 6.2 million tons of processed pork. On average, each person eats nearly 19 kilograms per year, an enormous amount, enough to practically fill the Grand Canyon if stacked continuously for 12 straight months. This irresistible appeal isn't accidental. Compared to beef, pork contains up to 1.5 times more fat and moisture, creating the signature tenderness, juiciness, and rich flavor found in ham, bacon, and sausages. To understand this fascination, we'll follow the journey of pork farming and processing, a complex chain stretching from the farm all the way to modern industrial production lines. The journey begins at Berkshire Pig Farms, a black pig breed renowned for its ability to produce intramuscular marbling, making it a strategic choice. These pigs are raised free-range on expansive pastures spanning hundreds of hectares, moving between designated grazing plots. During each grazing session, the herd forages while rooting the soil, returning organic manure, improving soil structure, activating microbial systems, and enhancing the pasture's moisture retention. The Berkshire diet combines native grasses, protein-rich legumes, grains, and agricultural byproducts, promoting muscle growth while preserving their ability to develop marbling. Thanks to ample exercise and slow natural growth, their fat penetrates deep into the meat rather than accumulating under the skin, resulting in tender, juicy, and flavorful pork, the very reason this breed is prized in the premium meat segment. Leaving the farm, the pigs enter the transportation system, a crucial link that determines both meat quality and the stability of this billion-dollar supply chain. To reduce stress and prevent injuries, specialized vehicles are equipped with non-slip sloped floors, straw bedding that absorbs shocks, and continuously circulating airflow. Temperature, humidity, and toxic gas sensors operate 24/7, ensuring that each journey delivers the pigs to the processing plant without carrying pathogens or biosecurity risks. And from here, the journey enters the most fascinating stage, where the planet's most widely consumed protein is reshaped inside modern processing lines. At the plant, premium Berkshire pigs enter a fully closed system, with each carcass carefully broken down into shoulder, ham, belly, and loin. High-quality cuts ready to be transformed into crispy bacon, aromatic ham, spicy pepperoni, or convenient canned meat. Here, advanced technology meets skilled craftsmanship, delivering top-tier flavors straight from the farm to the dining table. As one of the largest-scale pork products globally, ham has become a cash cow for the processing industry, generating up to $100 billion annually from the hind leg muscles, cuts with a balanced lean-to-fat ratio and excellent muscle structure. Before processing, the meat is trimmed of tendons and connective tissue and cut into small pieces in preparation for grinding. The meat is then moderately ground and thoroughly mixed with seasonings, creating a rich flavor while maintaining a smooth, lump-free texture. Once the mixture reaches the ideal consistency and thickness, it moves on to the shaping stage. In industrial lines using plastic casings, vacuum stuffing machines remove air bubbles before filling the meat, producing ham that is firm, smooth, and free of voids. With metal molds, the mixture is compressed tightly, forming a uniform block and eliminating air pockets, that ensuring a perfect texture for the final product. Immediately after stuffing and shaping, the ham blocks are transferred into cooking ovens to cook evenly, preserving both flavor and moisture. They are then cooled to stabilize the internal structure and removed from the molds, forming complete blocks, ready for the final finishing stage. Finally, the ham blocks go through automatic slicing machines, cut into thin slices just 1–2 millimeters thick. This thickness maximizes surface area, releases aroma more effectively, and ensures a tender bite when served cold. After slicing, the product is vacuum-packed or stored in protective gas environments, ready to appear on deli counters, especially in Europe. the market with the deepest and longest-standing ham consumption in the world. Meanwhile, on a different production line, bacon's treasure lies in the pork belly, a cut that accounts for only about 15% of the carcass weight, yet features the signature cross-section of alternating fat and lean layers that run continuously through the meat. The selected belly meat is then cured, primarily using a wet curing method. A brine solution is prepared in a precise ratio, combining salt, sugar, and spice extracts to balance saltiness and sweetness while stabilizing the meat's color. Multi-needle stainless steel injection systems pump the solution directly into the muscle tissue, with controlled depth and needle density, ensuring the seasoning penetrates evenly throughout the meat, not just on the surface. After curing, the meat is hung on racks and placed into smoking chambers, where temperatures are typically maintained between 50 to 70 degrees Celsius to cook the meat gradually without melting the fat. Smoke from woods such as hickory, oak, or apple imparts distinctive aromatic compounds while lightly drying the surface, helping the bacon achieve a stable color and long-lasting smoky flavor. Smoking times can range from a few hours to over 20 hours, depending on the recipe. After smoking, each piece of bacon is removed from the racks and passed through pressing machines to achieve a uniform thickness, making it easier to feed into the slicers. Following smoking, bacon is sliced by automated systems equipped with stainless steel blades, allowing thickness to be controlled down to the millimeter. On modern production lines, output can reach thousands of slices per hour, while maintaining consistency in size, fat-to-lean ratio, and smooth surface finish. From here, bacon becomes the flavor catalyst for any dish. Just 5 to 10 grams paired with a burger or eggs is enough to boost umami and richness, as the melting fat carries saltiness and smoky aroma across the palate. Next, we move on to pepperoni, the fermented sausage made from carefully selected back, shoulder, and belly cuts, destined to become the soul of millions of pizzas. The blended meat is passed through industrial grinders to achieve a uniform particle size of 3 to 5 millimeters, coarse enough to retain visible fat grains, yet fine enough to ensure even cooking, stable shaping, and sharp slices. Immediately afterward, the ground meat is transferred to industrial mixers to incorporate fermenting microorganisms and spices. Plants typically use lactic acid bacteria strains at extremely low densities per gram of mixture, precisely controlling the fermentation process. Dry spices are added along with concentrated liquid paprika, stabilizing the characteristic red color and developing the familiar mild spiciness. The entire mixture is mixed for 2 to 5 minutes at low speed, just enough to distribute ingredients evenly, without disrupting the meat's protein network. The mixed meat is then transferred to stuffing machines for shaping. The meat is pumped into sausage casings with precise weights for each segment, and the links are automatically twisted to form uniform chains of pepperoni. These chains are hung on conveyor lines, keeping the surface exposed to air and creating optimal conditions for biochemical reactions and subsequent heat treatment. From there, the pepperoni enters fermentation chambers, where controlled temperature and humidity activate the lactic acid bacteria, gradually lowering the pH to the ideal level and developing its distinct fermented flavor. Once this threshold is reached, the chamber settings are adjusted to inhibit further bacterial activity while lightly smoking the sausages with natural wood, finalizing both the flavor and the surface color. Next, the pepperoni is heated to fully cook, fixing the protein structure and establishing the desired firmness. Using high-speed rotary slicers, the finished product is cut into ultra-thin slices, often less than 2 millimeters, optimizing quick heat transfer, even fat melting, and the signature curling edges when baked on pizza. Completing the process, the dried pepperoni is fed into industrial pizza topping lines, where each deep red, fatty slice retains stability during baking, spreading a balanced, salty, fatty, spicy flavor across the pizza. This is especially notable in Domino's Pepperoni pizzas, a product line that has shaken the global pizza market, selling millions of slices every day. At the final stop of today's journey, there's Spam, a product so ubiquitous over its 80-plus-year history that its name has become synonymous with canned meat. But do you know what truly gives each can its distinctive texture and flavor? The journey begins when shoulder cuts are sent through industrial grinders at a controlled coarse level. Rather than pulverizing the meat completely, the grinding preserves the muscle fiber structure, creating a block that is both cohesive and retains the sensation of whole meat, a key difference that sets Spam apart from sausages. Next, the ground meat is transferred to the mixing area, where Spam's core recipe is applied. The ingredients include pork shoulder, salt, sugar, water, potato starch, and sodium nitrite. Salt extracts muscle proteins to create binding, sugar balances flavor, starch stabilizes the structure during heating, and nitrite controls microbial growth while preserving the signature pink color. The entire mixing process takes place in a chilled environment to minimize protein denaturation and ensure a uniform mixture before shaping. The mixed meat is then filled directly into metal cans with precise portioning, vacuum sealed, and hermetically closed to remove oxygen, reduce oxidation, and prepare for heat treatment. Immediately afterward, the cans are sent into a high-pressure steaming system and cooked for about 75 minutes, fully cooking the meat while eliminating harmful microorganisms, allowing the product to be safely preserved long-term without added preservatives. At the same time, the heat causes the proteins to coagulate, fixing a firm and uniform structure inside the can. Finally, the cans are rapidly cooled, cleaned, quality checked, and labeled with Spam's signature navy blue can and yellow lettering before being packed for global distribution. From the original pork shoulder, this process creates a canned product with a stable texture, consistent flavor, and a presence in over 40 countries worldwide. Here's a fun fact. Mention corned beef, and roughly 80% of people, even in the US, the UK, or Ireland, assume it has something to do with corn. In reality, there isn't a single kernel of corn in corned beef. The word corned comes from the Old English phrase corns of salt, referring to the large, corn-sized salt crystals used to cure the meat, the key technique that allowed beef to be stored for months before refrigeration existed. Compared with fresh beef, corned beef retains the same protein content but is noticeably saltier due to the deep curing process. This very trait made it responsible for more than 20% of the protein intake of British and American troops during World War II. The famous Frey Bentos cans not only sustained Allied forces, but became so strategically important that Nazi Germany sought every possible way to disrupt the supply lines carrying them. Today, Brazil, Argentina, and the United States form the three powerhouses dominating the global canned corned beef market. Though much smaller than the fresh beef industry, this crucial segment still generates over $9 billion annually and appears across every strategic distribution channel. From supermarkets and emergency stockpiles to humanitarian aid programs and long-range maritime logistics. And now let me take you to South America, the heartland of zebu cattle, where more than 80% of Brazil's national herd is raised on vast savanna pastures stretching for thousands of kilometers. Here, the dry tropical climate, mineral-rich grasses, and wide-open landscapes create an ecosystem that only zebu, with their large sweat glands, thick skin, and innate heat tolerance, can convert into steady, year-round weight gain. Zebu calves are born directly on pasture, nurse from their mothers during the early months, and develop a digestive system specialized for processing coarse forage, an advantage that allows them to gain nearly 1 kilogram per day on pasture alone, without costly grain-based rations. At around 18 months of age, when they approach 400 kilograms, they enter the final acceleration phase, focused on building muscle mass, tightening firmness, increasing lean meat yield, developing long muscle fibers, and maintaining structural stability, all ideal characteristics for industrial processing and large-scale production. Once they reach market weight, typically around 500 kilograms per animal, they are moved into high-throughput slaughter and grading facilities. The result? Brazil, powered by the Zebu Foundation, exports over 2.3 million tons of beef annually, securing its position as the world's largest supplier to beef processing systems, including the global corned beef production chain. Thanks to low production costs, consistent weight gain, and competitive emissions per kilogram of meat, even under intense heat, the Hanl has become the only cattle breed capable of operating smoothly at the massive scale needed to support a multi-billion-dollar industry. Leaving the pasture, the cattle officially enter a pivotal stage of transformation. From a living organism into the foundational raw material that begins the entire corned beef production process within the factory. At the start of the process, the cattle are placed in a restraint box and rendered unconscious using a captive bolt gun, aimed precisely at the center of the forehead. The shot instantly disrupts central nervous activity, causing the animal to lose consciousness almost immediately and feel no pain. This step is designed to ensure the highest level of humane slaughter. After the hide and internal organs are removed, the massive beef carcass, weighing hundreds of kilograms, is lifted onto the splitting line, where steel and precision meet in every cut. Industrial bandsaws, running at about 3,000 revolutions per minute, slice cleanly through the thick backbone while maintaining a straight, smooth, and perfectly aligned cut. Guided precisely along the spinal axis, the carcass separates into two symmetrical halves in both shape and muscle structure. This splitting step allows the meat to chill faster, handle more easily, and be butchered with greater accuracy, ensuring that every process afterward runs efficiently, consistently, and to the highest quality standards. After the carcass processing stage, the operation moves into the butchering phase, the direct foundation for corned beef production. Around 70% of the raw material comes from the brisket, the front chest area where the muscles work constantly as the animal stands and moves. This gives the meat thick, coarse fibers interlaced with marbled fat, creating its signature juiciness and rich flavor. The remaining portion mainly comes from the hind leg muscles, rich in connective tissue and collagen, components that help the meat hold its shape, stay tender, and develop a gelatinous texture during long cooking. Selecting the right muscle groups not only determines the tenderness, texture, and flavor absorption of corned beef, but also showcases the butcher's anatomical precision and refined knife sense. Those who can identify each muscle group simply by the grain's direction and the meat's subtle elasticity. Immediately afterward, the meat enters the curing stage, the critical phase that determines the flavor, color, and microbiological stability of corned beef. The meat blocks are placed into standard brine tanks containing water, salt, nitrite, and a precisely measured blend of spices. On average, each piece of meat absorbs 10 to 12% of its own weight in brine, allowing the solution to penetrate deep into every muscle fiber. At the same time, many factories use high-pressure brine injection systems with needles as fine as 1.2 millimeters to deliver the solution directly into the muscle tissue. This technique reduces the curing time from several days to just a few hours, while ensuring the salt concentration and signature pink color are evenly distributed throughout the entire batch. After the curing phase, the meat moves to the heating stage, where the entire marination process is activated and completed. The beef blocks are slow cooked in industrial steam kettles for 3 to 5 hours, depending on the thickness and muscle structure of each cut. Throughout cooking, the temperature is tightly controlled, maintained at a minimum of 70 degrees Celsius, the ideal point for protein coagulation, moisture retention, and the conversion of collagen into gelatin, which gives corned beef its signature tender, springy texture. Surrounding steam ensures even heat distribution, preventing surface drying or fiber shrinkage. Once cooked, the meat is gradually cooled to stabilize its structure before moving on to the next processing stages. After cooking, the process moves to the product forming stage, where the final texture of the corned beef is defined. Here, the meat is fed into an industrial shredding machine, equipped with dual augers rotating at over 1,800 revolutions per minute, combined with high-speed cutting blades that tear the fibers along their natural grain. The process is powerful enough to separate the strands, yet gentle enough to retain elasticity and internal moisture, ensuring that the meat inside the can remains loose, juicy, and authentically textured, much like hand-pulled beef. For the canned corned beef line, the process expands into a fully enclosed and highly precise production chain. An automatic compression system packs the meat into cans under high pressure, eliminating all residual air to prevent swelling during heating. Each can is measured to the gram, with a weight deviation of no more than 0.5%. After sealing, the entire batch is transferred to high-pressure steam retorts, where it is sterilized at 121 degrees Celsius for over 90 minutes. Conditions that eliminate microorganisms and allow the product to be stored safely for 3 to 5 years without preservatives. Once cooled, each can undergoes rigorous inspection, lid scanning, metal detection, and automated defect checks using optical sensors, before being coated, labeled, and packed for distribution. The entire operation integrates thermal technology, precision mechanics, and digital inspection, turning every can of corned beef into a perfectly stable, safe, and industrially refined product. Another approach is that, after marination, instead of being sent directly to the cooker, the meat is fed into a cutting machine where rotating spiral blades slice it into uniform chunks. These pieces are then packed into cans first, before being placed in high-pressure steam retorts, where the cooking process takes about 90 minutes at 120 degrees Celsius. This method helps preserve the meat's shape inside the can, ensures even flavor absorption, and reduces moisture loss. Compared to the traditional process, cooking first and shredding or cutting afterward, this approach saves energy, improves consistency, and is especially efficient for large-scale canned corned beef production. However, among the many choices at deli counters or cured meat shelves, one product is often mistaken for corned beef: pastrami, a smoked meat of Romanian Jewish origin, elevated by New York delis in the early 20th century into a culinary icon. Both dishes share the same foundation, the curing process using nitrite salt, mainly with cuts from the brisket, where thick fibers and strong connective tissues can withstand long cooking times while developing a deep, stable flavor. The key difference lies in how the flavor is defined. Corned beef develops its taste from the inside out, through brine infusion and slow cooking, creating a rich saltiness and a uniform, tender texture. Pastrami, by contrast, builds flavor from the outside in, coated in a dry spice rub, smoked at low heat to form a dark crust and layered smoky aroma, then steamed to achieve tenderness. The result is two distinct experiences, born from the same roots. In New York delis, pastrami is sliced fresh and served hot, releasing its full aroma and silky texture, while corned beef serves a different role, built for stability, longevity, and consistency, forming the backbone of the global canned meat industry for nearly a century. Now, let's begin with the fiercest hunt in the ocean, where humans face off against the planet's most notorious predator, the shark. The first step may seem simple, but determines success or failure: choosing the fishing ground. Coral reefs, nutrient-rich ocean currents, or areas where baitfish gather. Once the location is set, massive walls of net stretching for kilometers are cast into the sea, and when a shark swims by, its fins and steel jaws, symbols of its power, become the very chains that trap it. However, this method often harms non-target species, so many countries have tightened regulations, limiting soak time, mesh size, and requiring bycatch release devices to protect marine ecosystems. That's why modern fishermen are turning to longline fishing, a method that demands strength, skill, and determination. When a shark takes the bait, the deck instantly becomes a battlefield, where humans and apex predators struggle for dominance. The key to success lies in fresh bait and low-frequency sound devices that mimic baitfish movements to lure sharks in. On industrial vessels, sharks are processed right on deck, stunned, then injected with cold seawater or ice into their gills and body cavity to preserve peak freshness until the ship returns to port. The grouper, a sea giant with a blunt snout, a powerful body, and a cold, steel-like gaze, is now harvested mainly from large-scale offshore cage farms along the coasts of Southeast Asia. When the harvest season begins, massive sea cages are gradually narrowed, driving the groupers toward the center. From the deep water, 20 to 30 kg giants slowly emerge, their firm bodies and shimmering gold-and-silver scales glinting under the sunlight, showing they've reached peak physical condition. Fishermen work with swift yet precise movements, using soft, specialized nets to lift each fish gently out of the water. Every motion matters. Even a small scratch can reduce its market value. The freshly caught groupers are immediately placed into oxygenated seawater tanks, helping them stay healthy and calm before reaching the shore. On deck, the harvesting crew follows a strict protocol, checking the water's temperature and salinity, monitoring each fish's condition, and ensuring that every specimen meets quality standards. This marks the culmination of over 2 years of continuous rearing, monitoring, and care powered by modern aquaculture technology. Each harvest not only holds significant economic value, worth tens of thousands of dollars, but also reflects the seamless coordination between advanced farming techniques and the fisherman's expertise. These prized trophies are swiftly transported to processing facilities, ensuring they retain the same freshness as when they were still beneath the sea. In the cold northern waters of Japan and South Korea, when sea temperatures stabilize around April to May, sea pineapple, Halosynthia raretsai, farms enter their peak harvest season, the moment that marks the culmination of an entire year of cultivation. In highly mechanized farms, the harvest operates like a finely tuned assembly line. Long ropes densely covered with sea pineapples are hoisted out of the water using hydraulic cranes or pulley systems attached to specialized harvesting vessels. As each rope passes through the stripping chamber, hundreds of sea pineapples are automatically removed by a rotating drum system that combines twisting force and water pressure. The process takes only seconds but demands absolute precision to avoid damaging the spiny outer shell or the delicate inner tissue. Once detached, the sea pineapples are collected into large plastic containers or mesh bags, then lifted by hydraulic cranes and transported immediately to shore or to floating pre-processing stations near the farms. This minimizes transport time, prevents temperature-related spoilage, and preserves the natural freshness of these deep-water creatures. In smaller or traditional farms, however, semi-manual methods are still used. Each hanging rope may carry 100 to 150 mature sea pineapples, weighing up to 45 kilograms per line. During harvest, farmers use winches or manual pulleys to lift the ropes, securing them to the boat's sides or to large floating buoys to reduce impact. Dozens of lines are pulled up one after another, then slowly brought to shore, where coastal processing stations await. Though more labor-intensive, this traditional approach keeps the sea pineapples in their natural seawater environment until the final moment, preserving their fresh flavor and reducing biological stress before processing. Across tropical Asia, freshwater shrimp farms enter harvest season right after the rains, when pond water is lowered, ready for large-scale collection. It's the final stage of months of care, where skill, speed, and precision reach their peak. Farmers cast wide nets, working in rhythm. One group holds steady, while the other tightens the circle, driving thousands of shrimp toward the center. Beneath the surface, their firm, flicking bodies signal a perfect crop. Once enclosed, shrimp are quickly scooped up and transferred into oxygenated or chilled tanks to preserve freshness and vitality. Every step is closely supervised, from timing to post-harvest handling. For farmers, this is more than work. It's the culmination of a year's dedication, where each catch reflects their skill and pride. Off the coast of the North Atlantic, another hunt begins. The pursuit of the northern red shrimp, a rare species dwelling in some of the coldest and deepest waters on Earth. Out in the vast ocean, fishermen follow natural signs, seabirds circling above or sonar signals indicating shrimp layers at depths of 150 to 400 meters. Once the location is confirmed, the order to deploy the nets is given. Giant winches and pulley systems lower funnel-shaped trawl nets to the seabed. Two large otter boards keep the mouth open as it sweeps across soft sediment where red shrimp hide. Inside, biological sorting devices automatically release turtles and other bycatch, ensuring a sustainable and responsible harvest. After 3 to 6 hours, the nets are hauled back up, bulging and heavy, a sure sign of a successful catch. The red-pink shrimp spill into the loading hopper on deck, where the automated processing system immediately takes over. Washing, grading, and flash freezing at -40°C to preserve their natural color and firm texture. From the moment they leave the deep sea to the time they are stored in onboard cold rooms, the entire process takes just a few minutes, a testament to the precision, speed, and technological power of modern Northern European fisheries. Continuing our journey, let's head out to the vast Atlantic Ocean, where specialized fishing vessels surge through the waves, launching a spectacular pursuit known as the mackerel hunt. In this modern chase, no method proves more effective or breathtaking than the purse seine. A massive net stretching hundreds of meters, released into the sea to form a tightening circle, like an invisible trap beneath the waves. Speed is the key to success. The faster the net closes, the slimmer the fish's chance of escape. As the final line pulls taut like a steel noose, tens of tons of shimmering mackerel are enclosed within a swirling silver mass, churning violently beneath the foaming water. Powerful hydraulic cranes roar to life, rhythmically hoisting each heavy catch and pouring it straight into deep freezing holds kept at 22°C, preserving their pristine freshness. In less than 30 minutes, a single haul can yield over 200 tons of fish, a bounty that once took an entire fishing village weeks to gather. It is not merely the triumph of technology, but a relentless duel between humankind and the sea. Among the hundreds of fish species in the ocean, only the pufferfish can make fishermen both crave and fear it. Catching tuna demands speed, mackerel requires nets, but catching pufferfish? That's like playing with knives on a stormy deck, where every move flirts with danger amid freezing winds and crashing waves. The hunt begins with the most crucial element, bait. But not just any bait will do. Pufferfish are notoriously picky. Fishermen must use freshly caught mackerel, carefully cleaned, trimmed into perfect cubes, and salted to preserve freshness. If the mackerel oil turns rancid, the pufferfish won't even come close. Each day, up to 20,000 bait cubes are prepared and packed into 250 ice boxes, all for a single 48-kilometer-long line, strung with over 20,000 razor-sharp steel hooks. Once the bait is ready, the massive line sinks slowly into the sea, its thousands of hooks forming an invisible web beneath the surface. But that's when the real risk begins. A sudden gust of wind, a lost buoy, and hundreds of hooks, worth thousands of dollars, vanish into the abyss. Many fishermen have gone bankrupt after a single unexpected storm. Catching pufferfish isn't just a trade, it's a high-stakes gamble with the ocean, where the line between ruin and fortune is drawn by just one pull of the hook. Tilapia, the most widely farmed white fish on the planet, with an annual yield exceeding 6 million tons, is often called the chicken of aquaculture. It's primarily harvested in the warm waters of Asia, Africa, and Latin America, where stable climates and abundant freshwater create ideal growing conditions. Harvesting is carried out using large seine nets or specialized fish pumps. As tens of thousands of fish are drawn together, the surface comes alive with movement. The harvest crew works in perfect sync, closing the net gradually, herding the fish into a central area. Every motion must be precise, fast enough to prevent escape, yet gentle enough to avoid bruising scales or breaking fins. Once gathered, the fish are transferred directly into aerated tanker trucks, the first-class cabins of aquaculture transport. Inside, water temperature and oxygen levels are carefully regulated, keeping the fish healthy and alive all the way to the processing plant. From netting to transport and handling, every step is timed to perfection, because just a few minutes' delay can affect meat quality due to biological stress. For fish farmers, this isn't merely a technical process, but a code of respect for the creatures they raise and for the hard work that sustains their livelihood. Unlike white clams or scallops, which are often harvested on an industrial scale using sand suction dredgers or powerful trawl boats, blood cockles remain largely tied to traditional manual harvesting methods, a rhythm deeply woven into coastal life. When the tide recedes to its lowest point, a narrow 2-3 hour window each day, hundreds of workers spread across the mudflats, bent low, hands digging and raking. Some use 10 to 12-toothed steel hooks attached to long handles, gently scraping the soft mud to uncover shells buried 5 to 10 centimeters deep. Every movement requires precision and sensitivity. Too much force, and the shell breaks. Too little, and it slips deeper into the mud, losing its market value. Yet, to meet the rising global demand, many coastal farms have begun adopting controlled mechanization, integrating modern dragnet systems. Heavy nets are lowered into the muddy seabed, plowing long strips and gathering clusters of cockles, which are hoisted up by hydraulic cranes. Within minutes, hundreds of kilograms of shellfish are dumped into onboard bins, then immediately washed, sorted, and packed on the vessel itself. Compared to the traditional sun-drenched hand-picking on muddy shores, this new method is 5 to 10 times more efficient, yielding 5 to 8 tons per day. But that speed comes at a price. High investment costs and the risk of disturbing the seabed ecosystem, threatening plankton populations and natural broodstocks that sustain future harvests. To create a finished piece of stockfish, time matters more than any technology. Fresh cod must be hung outdoors for 3 to 5 months, then left to further mature so its flavor can fully develop. This harsh process reduces 5 kilograms of fresh fish to just 1 kilogram of stockfish. Each piece a crystallization of loss and patience. In its dried state, stockfish is almost wood-like, impossible to cook immediately. It must be soaked in water for days to awaken the structure of the flesh. Once revived, it becomes a nutrient-dense food, rich in protein and minerals, having sustained sailors on long voyages across icy oceans for centuries. Today, stockfish has moved far beyond its role as survival food. In Italy, especially in Venice and the Veneto region, it is a prized ingredient in traditional cuisine. In Africa, particularly Nigeria, stockfish is revered as a powerful umami seasoning, deeply woven into everyday cooking. At present, premium stockfish can reach prices of up to $150 per kilogram, rivaling or even surpassing Alaskan king crab. This price reflects a clear market paradox: limited supply paired with ever-growing value. Stockfish exports alone generate nearly $85 million, transforming a seemingly humble dried fish into a global luxury commodity. The answer to the high price of stockfish begins with the Arctic scray cod season, a migration of more than 1,000 kilometers from the Barents Sea to Norway's coastal waters, and one of the few moments each year when the fish reaches peak quality. At this stage, scray cod has a high lean meat ratio, low fat content, and muscle fibers firm enough to withstand natural air drying. The core fishing season starts in early spring and lasts only 3 to 4 months, forcing vessels to head out continuously. Miss this narrow window and the cod moves past its ideal biological phase. Muscle tissue retains more water and becomes unsuitable for long-term drying. As the schools arrive near shore to spawn, fishermen enter the season using 2 traditional methods. The most common is gill netting, nets suspended in the water column and anchored along ocean currents. Cod are typically caught horizontally by the gills, minimizing body impact against the net and reducing surface damage during hauls that can last dozens of continuous hours. The second method is long lining, lines stretching several kilometers and fitted with thousands of hooks. While yields are lower, each fish is hauled up individually along a vertical axis, avoiding compression. Reduced mechanical stress prevents skin abrasion, blood pooling within muscle fibers, and structural damage, critical conditions for enduring more than 100 days of wind drying. All of this takes place in the volatile Arctic seas. On calm days, a small fishing vessel may land 1 to 3 tons of cod. On others, boats return empty-handed due to strong winds, heavy swells, or shifting fish stocks. It is precisely this uncertainty that has kept stockfish from ever becoming a mass-market product. Yet it has endured for centuries, sustained by perfect timing, careful harvesting, and a measure of luck granted by the sea itself. But the catch is only half the journey. Right on the deck, as the cod are hauled up from the icy depths, a small hand processing line is already in motion. In temperatures hovering around -4 degrees Celsius, the fishermen work tirelessly amid the biting wind and spray. Each voyage brings in over 15 tons of cod, and every fish is handled immediately on site, usually by cutting the gills or making a shallow incision near the neck to drain the blood. This quick treatment helps preserve the freshness, stabilize the pH of the flesh, and prevent bacterial growth throughout the long, restless hours at sea. When the vessel docks, crates of cod are immediately transferred to the processing plant by the harbor. The chill of the sea still clings to their scales as they move along the first conveyor line, a short 50-meter path linking the ocean straight to the cutting tables. Here, the full processing begins. Each fish is beheaded, gutted, and cleaned with swift, precise strokes. Skilled workers use slender knives, slicing diagonally along the belly to open the cavity without rupturing the gallbladder or intestines, preserving the fish's clean flavor and bright flesh. Each worker can process up to 1,200 fish during an 8-hour shift, a rhythm sustained only by years of experience and muscle memory. The entrails are removed in a single decisive motion, halting internal decay, and the fish are then rinsed in seawater, chilled to 2 degrees Celsius to stabilize the texture. From there, they're laid on racks or sent to drying, freezing, or salting rooms, depending on the final product. The entire process takes only a few minutes, yet every precise cut determines the quality of the catch that will become premium stockfish, celebrated across Northern Europe as the purest taste of the cold sea. From this point, the journey of stockfish enters its defining stage, the moment when its true value takes shape in a way no other dried fish can replicate. After processing, thousands of cod are hung outdoors on vast wooden racks, stretching for nearly 300 meters along the Lofoten shoreline, where the cold North Atlantic wind blows day and night. The drying frames are engineered with precision. Sturdy A-shaped beams disperse wind pressure and weight, while the high, open crossbars allow ocean air to circulate freely around each hanging pair, ensuring a natural yet meticulously controlled drying process. Because the body and head dry at different rates, they are hung separately, but all follow the same traditional posture, head down, belly open, allowing gravity to draw out moisture evenly. Over the course of 2,800 hours with air temperatures rarely rising above 5 degrees Celsius, and humidity hovering around 70%, the fish gradually dry from the inside out without ever spoiling. The muscle fibers tighten, proteins and collagen fuse together, forming a dense, elastic texture, the secret that allows stockfish to keep naturally for more than 3 years without a grain of salt or any preservative. When the fish reach their equilibrium point, reduced to roughly 1/3 of their original weight, They are moved into curing lofts to lock in moisture balance and flavor. Under the pale northern light, thousands of white cod hang in rows like an inverted forest swaying in the wind, monumental yet silent, marking the near completion of the journey from deep ocean to Norway's most revered delicacy, the legendary stockfish.